right, today we're going to talk about section 9.2. Series. A series, if you remember from pre-calculus, is when you're adding up the terms of the sequence. In section 9.2, the first big idea that's in your notes is a sequence of partial sums. I'm happy to come in and have a discussion with you about that, but we won't use that method to find a sum. It's used for a lot of the proofs that support the methods we are going to use. So again, I'm happy to come in and talk. It's exciting to talk about. But I want to start with the second thing on our notes, geometric series. I want to bring that back from pre-calculus. And in calculus, we're only looking at infinite sums. So if I want to know a geometric series, we may remember that sigma, a geometric series, is written as a sub 1 times r to the n minus 1. Now, we'll be able to recognize it because it's going to be some number raised to an n or raised to the n minus 1 power. The formula that we had for the infinite sum of a geometric series is that it's the first term divided by 1 minus r. Now, I think in pre-calculus you may have put a sub 0 or a sub 1 there. I wrote first term because it depends. If this starts at 1, my first term is when I plug in 1. If this starts at 2, my first term is a sub 2. So it depends on what you're given. Now you may remember, as it says on your sheet, that the infinite sum exists if r, or the absolute value of r, is less than 1. But if the absolute value of r is greater than 1, the sum does not exist. Therefore, if r is less than 1, my series converges to whatever that sum is. And if r is bigger than 1, then the series diverges. We have a couple examples. We have 3 examples, so let's look at these 3 examples. We have 2/3 to the n minus 1 from 1 to infinity. Well, I look at that and I recognize it's geometric because it's some number raised to a power, and almost always this r is going to be a fraction. That's the other kind of tell. Not always, but usually. And r is less than 1, so I know this converges, and we can find s. S is equal to the first term. We'll plug in 1. I get 2/3 to the 0, which is 1, over 1 minus r. So that's going to give me 1 over 1/3, which is 3. The second series on your examples diverges because r is 5/3, which is more than 1. So here, this one diverges because r, which is 5/3, is greater than 1. And we're going to look at the third one. Third example is the series from n equals 1 to infinity of 8 times negative 1/4 to the n. Now, r, the absolute value of r anyway, r is negative 1/4. The absolute value of that is less than 1. Therefore, we know that this converges. It's going to converge to s equals, well, what's the first term? If I plug in 1, I get negative 1/4 times 8, which is negative 2, divided by 1 minus r, which happens to be negative 1/4. So s is negative 2 divided by 5/4, can do our arithmetic. Times 4/5. So my sum is -8/5. What is that saying? Well, it's saying if I wrote out the terms to this sequence or series and added them up forever and ever, I would get no bigger than -8/5. And I get really, really close to -8/5. So, one of the important series in section 9.2 is my geometric series. The second big important series that we have is a telescoping series. You can look at number 3 in your notes. In telescoping, you want to think of like a telescope, you know, ones that can pull out and collapse. So telescoping series here, we want to think about something that collapses. In the example given in your notes, you have b1 minus b sub 2 plus b sub 2 minus b sub 3. And that pattern continues forever. And so you notice second and the third cancel out, fourth and the fifth. And so you're left with the very first term and whatever the very last term would be. But it's infinite, so we don't know. So we express the sum, in this case, is a sub 1 minus the limit as n approaches infinity of whatever that last term would be. Now, we can generalize this for all telescoping series and say that it's the terms that do not cancel minus the limit as n approaches infinity of that last term. Now, how am I going to recognize a telescoping series? That becomes important. Like I can recognize a geometric series because it's r to a power, and r is generally a fraction. I can recognize a telescoping series because it's going to be the difference of two fractions. For example, the number 1, they give us the series from n equals 1 to infinity of 1 over n minus 1 over n plus 1. With every telescoping series, I strongly recommend write out a few terms. That way, you can determine easily which terms cancel out, which terms stay. So if n is 1, I get 1 minus a half. When n is 2, I get 1/2 minus a third. When n is 3, I get 1/3 minus a fourth, etc. forever. So I notice that -1/2, +1/2 will cancel, -1/3, +1/3 will cancel, etc. So my sum will be 1 minus the limit as n approaches infinity of 1 over n plus 1. Well, this limit is going to go to 0, and it should always go to 0 if I'm telescoping. So in this case, my sum is 1, because that was the only term that did not cancel out. Now, if you look at example number 2, you may be saying to yourself, why is that in this section? It's not written as two fractions. But you may notice the bottom can be factored. So we have this series, forgot what it was, 4n squared minus 1. Well, 4n squared minus 1 can be written as 2n minus 1 and 2n plus 1. We learned in section 8.5, we can rewrite that as two separate fractions by using partial fractions. So we first need to figure out what two fractions did these start out as. So we're going to do our partial fractions. E over 2n plus 1. Multiply both sides by the common denominator. We're left with 1 is equal to a times 2n plus 1